Okay, let's illustrate Newton's method with a couple of examples. So here, we're looking for roots of a polynomial. Consider this fourth degree polynomial. Rumor has it, this can be factored as 8 times x minus r1, x minus r2, x minus r3, x minus r4. The r's, because these, the r's, because these will be roots of the polynomial, which is perfect. We'll set the polynomial equal to 0. That's how you find roots, and that's exactly what Newton's method can numerically approximate. Fourth degree polynomial, by the fundamental theorem of algebra, is guaranteed to have 4 roots. The problem is they might not all be real numbers. Here, they've given us a graph of this function, and we can see the 4 intercepts of the x-axis where that function is 0. So indeed, we got 4 real roots. So we want to numerically approximate those. In this graph, we see that it looks like a -1 or something close to -1 is a root of the polynomial. Actually, we can plug -1 in and see that it's not a root of the polynomial, nor is 2, but it looks like there's a root really close to 2. So we'll label these R1, R2, R3, and R4. For R1, we'll start as an initial guess the point -1. For R4, we'll start as an initial guess 2. And those should be fairly close if this is a good graph of the function. For this one, it's a little bit bigger than 0. We'll start at 0. Might need to iterate it a little bit more. Maybe we won't, and just compare how accurate it is to the other approximations. And for this one, how about we start at 1? This should take us to this root. I could make a better initial guess than 1. I'm going to start with 1 for the sake of illustration. Maybe like 2/3 would be a better approximation of that particular root, or 1/2 maybe. But I'm going to start at 1. And I expect to have to iterate it a little bit more to get more decimals of accuracy is how we'll rate the accuracy. Okay, so first, we'll let f of x be 8x to the 4th power minus 14x cubed minus 9x squared plus 11x minus 1. Let it be this polynomial function. Then finding a root of that polynomial is the same as solving the equation f of x equals 0. We have to be able to put the question in the form f of x equals 0 to use Newton's method. Okay, so we'll need the derivative. So differentiating, just a polynomial, straightforward differentiation. For the first root, notice that -1 looks like an approximate root. So we'll start with x sub 0 equals -1, and we'll make a table of numerical approximations. I'm going to round this table to 5 decimal places. They mentioned 5 decimal places in a previous example instead of using exact values, because exact values would be an extremely awkward thing to deal with. So we'll deal with just approximations. I'm saddened by that, but what you going to do? It's intended not to be done so much by hand. We could write a little piece of software that would whip through this in no time. Okay, so we'll start with start with the x sub 0 equal to -1. So start with our first approximation, -1. We'll plug that into the function. We'll plug that into the derivative. Just happen to have the function and the derivative sitting up here. So I'm plugging -1 in f and f prime, producing these two outputs. Newton's method says x sub n plus 1 is x sub n minus f of x sub n over f prime of x sub n. So we'll take that first guess, -1, and subtract f of -1, 1, divided by f prime of -1, which is -45. Keep an eye on the signs. So we get -1 minus 1 over -45. So we've actually added a tiny bit to -1. And if you look closely at the graph, it seems that the intercept was a little bit a little bit bigger than -1. And we're getting out negative to 5 decimal places, 0.97778. Yeah, something a little bit to the right of 1. And the graph looked like that, that's where its intercept was. Let's do it again. Okay, let's take that -44 over 45. I can plug precisely that into the function, but I want to talk decimal approximations to see how things are changing from step to step. I plug the -44 over 45 in, produces something like this. Plug it into the derivative, produces something like that. And again, we'll take the previous, the x sub 1, -44 over 45, and we'll subtract f of that value given here divided by f prime of that value given here. Do the arithmetic, we get negative 0.97683. Not that the number really means anything to us, but it didn't change very much from here to here. The first time it changed by what? About 2/100ths. This time it changed by about 1/1000th. You want more decimals of accuracy? Go right ahead and iterate it some more. We're pretty close, it looks like, to a root. So we'll go to x sub 2, n equals 1. Remember, in this last column, just the table computes x sub 1 plus 1. So this is x sub 2. So we got x sub 2 approximately equal to this, to 5 decimal places. So we'll take that to be that first root, r sub 1. Let's do that again. Let's do it on the far right, that root that we thought was close to 2. So we'll do the same thing. That way we were calling r sub 4 because we were listing the roots in order. So the indices look out of order on what we're doing here in terms of the r's, but I got my reasons. Again, here's f of x and f prime of x. It looks like there's a solution around x equals 2. So let's apply Newton's method starting at 2. We plug 2 in. We get 1 out. You look at the graph of that function. It doesn't look like we're getting 1 out at the point 2. So maybe their graph isn't quite so precise, but the arithmetic will reveal to several decimal places this root. We plug 1 into the function. We plug 1 into the derivative. We get 1 and 63. So we'll take 2 minus 1 over 63. Precisely, that's 125 over 63. It's about 1.98412. Okay, it's a little bit less than 2. If you look at the graph, it looks like the intercept is a little bit less than 2. I'm calling the graph somewhat into suspicion, and that I'm not going to be able to tell the difference between 2 and 1.98 on a graph at the size of the one they gave us. But there's what we get out after one iteration of Newton's method. Do it again. So we'll plug that, 125 over 63. If you like precise values, I may as well use them while I can. And then I'll need a numerical approximation of what comes out of the function and its derivative at 125 over 63. These are the two values we get. We'll take the previous value, 125 over 63, and subtract this divided by that. Produces this. It got a little bit smaller still. So it seems to be decreasing still, but it didn't change by much. Going from x sub 0, 2 to x sub 1, it changed by about 2/100ths, less than that. Going from x sub 1 to x sub 2, it changed by a bit less than 1/1000th. More in the neighborhood of, 4/10,000ths. Just eyeballing it and looking for levels of accuracy. It didn't change much. So let's take that as that root r sub 4. I'll ask some software what it thinks the roots are to 5 decimal places, and then we'll compare what they got to what we got. Granted, if you want more decimals of accuracy, it would be wise to iterate the process more. This is tedious arithmetic, though. Nobody does this by hand, except in Calculus 1. All right, what about that root that was close to 0? Here's the function, here's the derivative. We'll start with 0. We're looking for a root that's a little bit greater than 0, and we'll apply the technique. I like 0. The arithmetic is easy. Produces 1 over 11 on one iteration, 0.09, so it jumped by that much from 0. Let's plug 1/11th in. Now the x of one value, plug it into the function, and its derivative produces these two numbers. Plug those into Newton's method. It increases a little bit more. Notice it increased from 0 to 0.09-ish, and then it increased from that to 0.10026, so it's still increasing a little bit. The geometry might make some sense to you. And let's see, from here to here, it didn't change by very much. Maybe 1/100th. Changed by something on the order of 1/100th. Let's take that as x sub 2. I could iterate it a third time. Remember, our initial guess this time, based on the graph of the function, I don't think it's quite as good as the first guess on those other two roots. We iterated those 2 times. Let's iterate this one 2 times as well and see if that's right. Let's see if this one's not quite as accurate as the others. Whose fault is this? My initial guess of 0. I could have done better than that. Another one where, in the final root, we observed that there was a root around, what, like 2/3 or something? And I said, let's start at 1. Now I know I could do better for an initial value than 1. 2/3 would be a better starting point. I'm starting with 1. Even by starting so far away, if I iterate more, I still expect this to work. Some things can go wrong with Newton's method, but the fact that I'm going into this knowing that my first approximation is a bit crude, we'll just iterate it more times. I'll iterate it 1 more time. So we'll start at 1. Arithmetic with 1 is easy. That takes 1 and changes it to Newton's method outputs 0.7. Okay, so it dropped by quite a bit. It dropped by 30%. It dropped from 1 to 0.7-ish. Let's take that 0.7-ish, 12/17, and plug that into the function and into its derivative. We actually got 12/17 out over here. I'll use a precise value and then take numerical approximations of that. Beyond this, the rational numbers are just too outrageous. So we'll stick with decimal approximations in the next step. Another reason to do another step to illustrate that. We'll take the 12/17 and adjust it according to Newton's method. It dropped a bit more this time to 0.648. So this time it only dropped by about 5/100ths. Let's iterate it again. All right, so we'll take this output, 0.64809, and we'll plug that into the function and plug that into the derivative. That instead of the precise corresponding rational value, because a rational value was outrageously complicated. So we'll cut it to 5 decimal places, plug that in, produce some approximate outputs, use Newton's method to adjust the previous result. This time it gives out 0.64280. This time it changed by what, about 6/1000ths. So it's changing by less. What's happening behind the scenes is Newton's method is getting you closer and closer, in these cases, to the actual root. So I see the numbers change by a smaller amount as the process goes on. If you don't see that either, something bad's happening or your arithmetic is off. And it's easy enough to make arithmetic mistakes with these icky numbers in a calculator. But I'm going to take that third output as the root r sub 3. Okay, so we found all 4 roots. We've approximated all 4 roots. And there's the values we got. Let me ask some software. I'm going to ask Wolfram Alpha about this. And Wolfram Alpha tells us that the approximate roots are to 5 decimal places. These numbers here, how'd we do? Pretty good on that first one. we're only one part in, tenths, hundreds, thousandths, 10,000ths, 1/100,000th off. Pretty good. We only iterated Newton's method twice. It's because we started so close to a root. And look at the graph. It does seem to indicate it has an intercept a little bit to the right of -1. This is a little bit right of -1. The last one, I expected to have some confidence in that one when we took the 2. In fact, these agree to 5 decimal places. So to 5 decimal places, we looks like we're on it in this one. Here, this was R sub 2. We got 0.11026, 0.10036. Wolfram Alpha gets. Standard software, there's links in the notes to Wolfram Alpha or on the syllabus. Here we're within tenths, hundreds, thousandths, 1/10,000th, so not nearly as good as we did with R1, but this is the one where I only iterated it twice, and still, we're not bad. We've got 3 decimal places. We don't have 4 decimal places, but we got 3 decimal places of accuracy. I could have iterated it more, like we did looking for R sub 3. In R sub 3, I started knowingly with not a very good initial value, so I iterated it more. I iterated it one more time. They tell us 0.64274. We got 0.64280. Okay, so even on that one, we got 3 decimal places of accuracy. We didn't get 4 decimal places of accuracy if I round these off. So still not bad. I could have iterated this one more until I see the numbers settle down more. If I keep a fixed number of decimals, it'll probably, at some point, it'll look fixed. Now there's more going on that I'm not looking at because I'm chopping things to, say, 5 decimal places. Hey, how did Wolfram Alpha do this? May well have done it using Newton's method. Now there's other numerical techniques more sophisticated than Newton's method, but Newton's method is a powerful method, and whatever Wolfram Alpha did was likely some iterative technique, maybe more sophisticated than Newton's method, maybe not, maybe they actually use Newton's method. These are fairly simple functions, just polynomials, so finding their roots, numerically approximating their roots is not a complicated thing, and Newton's method is a good place to start. Let's do another one, a transcendental function. The question is, does cosine 3x ever equal x? Give reasons. Use Newton's method to find where. The answer must be yes, but we'll have to justify that. We want to make sure that these things actually do cross before we go looking for where they cross. A very careful graph of y equals cosine 3x and y equals x suggests they actually intersect in 3 points. One very obvious point, and I got a fair idea of where it is. It's between 0 and pi thirds, if I believe this picture. We need an argument more sophisticated than a picture, though. And it looks like it may intersect at a couple of points over here. They wanted to know if cosine 3x ever equals x, if these two curves ever intersect. The book referred to it as intersecting curves. Let's look for this one. This one, I don't quite know where to start. And I probably don't have a very good idea at all how to find both of these. Let's find this one. They ask us, ever do they intersect? Yeah, let's look here. These other 2 points, just between you and me, when the authors chose this as a question, I don't think they had those 2 in mind. Okay, so we'll show there is actually a point of intersection between these 2 curves, between 0 and pi thirds, say. How do you know? Intermediate value theorem. Both of these functions, x and cosine x, are continuous. We'll look at their difference. But hey, the blue one is on top over here, and on the bottom over here, well, somewhere in between they had to meet. That's an intermediate value theorem argument. More precisely, define a function f to be cosine 3x minus x. So we'll have cosine 3x equal to x when we have this function equal to 0. I gotta encode the question asked in terms of one that can be addressed by an equation of the form f of x equals 0 if I'm going to use Newton's method. Let's try that. First off, if we plug 0 into the function f, we get out 1, which is positive. If we plug pi thirds into the function f, we get out -1 minus pi thirds, which is negative. It's positive in one place, it's negative in another. That's a continuous function. Continuity makes it all work. That's a continuous function. Intermediate value theorem tells you somewhere between 0 and pi thirds, there must be a there must be a solution to the equation f of x equals 0. The function must take on the value 0, 0 being intermediate to these two output values. That is, there's an r somewhere in there such that f of r equals 0. So, does cosine x ever equal x? Yes, somewhere in there. Apparently some other places as well. They want it ever. I'm going with the easy one. Part B, use Newton's method to find, really to approximate where they're equal. All right, based on the graph, we'll start, say, at x sub 0 equals pi 6. Let's look at the picture one more time. Okay, here's the graph. Pi 6 would be halfway between here, to be somewhere over here. The gap is actually fairly big. Remember, I'm looking for the gap between these two. I'm trying to make that 0. They're rather far apart at pi 6. I could do better at maybe pi 12s, a quarter of the distance from 0 to pi thirds, maybe pi 12s. Is pi 12 a special angle? Yeah, I can use some half angle formulas and find the precise values. Precise values aren't really the spirit of this Newton's method stuff. And I start at pi 6 because it's a special angle, and then we'll have to translate over or transfer over to decimals here, frowny emoji again. Let's start at pi 6 because I typeset all this stuff using pi 6 as an initial value. And we'll make a table of numerical approximations. We'll have to round it to 5 decimal places. They've been using 5 decimal places. We'll have to use decimal approximations after that first precise value of pi 6. The function we're dealing with is cosine 3x minus x. Its derivative is -3 sine 3x minus 1. Derivative of cosine is negative sine, and the chain rule throws a 3 outside of that. The negative came from differentiating a cofunction. 3 came from the chain rule and the 3x inside. And we got a -1 over here on the side. Okay, so that's the plan. Here's the initial value, pi 6. Numerically, that's a little bit bigger than a half. So I'm sorry, a little bit bigger than a half. The negative sign should not be there, of course. That's a boo-boo typo there. We'll take cosine of that. 3 times that's cosine of pi halves, which is 0. So we actually get 0 minus the pi 6. I do need a negative here. Typo there. I will fix that in the notes. But this one does have a negative because we're subtracting. We get negative pi 6 at this one. We'll take the pi 6, plug it into the derivative. That produces a nice, neat -4. I got arguably nice numbers out of both of these. This one's pi 6 and this one is -4. I'll plug those numbers in and then it's off to numerical approximations. So we'll take pi 6, subtract from it this divided by that. Notice we get little numbers over here, and if we're lucky, we get relatively big numbers over here. I'm going to divide the little numbers by the big numbers and get really little numbers. And that's how much our guesses are changing. The x sub i's are changing by this divided by that. Well, the smaller this is and the bigger that is, the smaller that they change by will be. And we want that to be small because we want to get close to a root. Okay, so we'll plug in this value and that value. It's written precisely here. That'll give us approximately 0.39270. So it changed from, cover up that negative, it changed from about 0.52 to 0.39. So it dropped by what, 0.13-ish. That's a pretty sizable change. let's, well, but remember, my initial guess wasn't very good. Let's take that, plug it into the function, plug it into the derivative, do the modification in the arithmetic. We get 0.39004. Okay, it changed by about 0.003-ish, 0.0027-ish, which is what, 20, well, 27 ten thousandths, is that right? Let's do it again. We'll plug that number in, iterate yet again. Actually, it doesn't change. Look how small the value of the function was when we plugged in 0.39004. I actually added an extra decimal of accuracy here. If I round this to 5 decimal places, it's 0 rounded to 5 decimal places. So it's not actually equal to 0, but to 5 decimal places, it's 0. So I added an extra decimal there. We're trying to see when this function takes on the value 0. Well, it's awfully close there. So close, there's no change in this to 5 decimal places. There's changes if you want more decimal places. So you want more decimal places, keep up with it throughout, and you probably have to iterate it more to get more decimals of accuracy. In the back of my mind, I'm worried about maybe round off error if I just go insane iterating this hundreds of times. Repeated iteration isn't always a good thing. These are kind of the topics you would explore in a numerical analysis class. Round off error becomes an issue. So we'll certainly take that, 0.39004, we'll take that as our approximation of the solution to the equation cosine 3x equals x. That should be accurate to 5 decimal places. I'll go ask Wolfram Alpha what they think and try to coax some more decimals out of them. You can get many decimals from the Wolfram Alpha online free software. You can't get everything Wolfram Alpha has just over the internet. They're trying to sell you copies of their software. But I can get several decimals, more than 5. Here's a few more, and well, we're spot on to 5 decimal places. If you want more decimals of accuracy, you should have kept up with more all along, and you probably have to iterate this more times. Oh, Wolfram Alpha also tells us the other 2 solutions. Look, they're fairly close together. That picture I had up front must have been reasonably accurate. Yeah, let's not worry about finding those. It'd be quite difficult, because these are close together, probably to distinguish between the 2. When I applied Newton's method, I'd have to be awfully careful in my choice of x sub 0 to determine one of these and not the other. Also, both of these are fairly close to a place where that cosine function has a horizontal tangent line, and I worry about maybe finding places where f prime is 0. But anywho, there's the other 2 solutions. They ask us if they ever intersect. They do. To 5 decimal places, they intersect there. Okay, this is, in my opinion, fairly unelegant stuff, this numerical crunching number stuff. Nobody does this by hand, except in Calculus 1 to illustrate the technique. Really, the important idea is the geometry about tangent lines and finding intercepts. But that will take care of that. That's our one and only numerical technique. We're going to shift gears going into the next section and do antiderivatives there. And the remainder of the course will be closely related to some of this antiderivative ideas. I'll see you in the next section. Have a nice day.